Start with a list of fractions. 1, then minus 1/2, then plus 1/3, then minus 1/4, plus 1/5, minus 1/6, and on forever. The signs flip every step, and the pieces you are adding get smaller and smaller. Add them up in order and watch the running total. After one term, you are at 1. Subtract 1/2, and you drop to 0.5. Add 1/3, back up to about 0.83. Take 1/4, down to about 0.58. The total keeps stepping up and down, but the steps shrink, and it closes in on one specific value. That value is the natural logarithm of 2, about 0.693. The more terms you add, the tighter the running total hugs that number. After 100 terms, you are already within 1/100th of it. After 10,000 terms, you are closer still. This series has a definite sum. Feed it in the order written, and it lands on 0.693 every time. This is a famous series, and for 200 years nobody worried about it. It converges, it has a clean value, and that value is a number people care about. Everything looks settled, but there is a loose thread here, and pulling on it unravels something surprising about what it even means to add up infinitely many numbers. Now take that exact same infinite list of fractions. Every single piece is still there. 1, 1/2, 1/3, 1/4, all of them, the same signs attached. The only thing changing is the order you feed them in. Here is the new order. Take 2 positive terms, then 1 negative term, then repeat that forever. So 1 plus 1/3, then minus 1/2, then 1/5 plus 1/7, then minus 1/4, then 1/9 plus 1/11, then minus 1/6, 2 up, 1 down, every round. Nothing has been added, nothing has been removed. It is the same fractions from before, just marched in a different sequence. And you would expect the same total, because addition is not supposed to care about order. Watch the running total this time. It climbs higher. It settles on 1.04, which is exactly 3/2 of the natural logarithm of 2. Same numbers, and the answer grew by half again. You can even see, roughly, why it climbs. In the original order, every positive term was chased immediately by a negative one that ate most of it. Here, 2 positives get to pile up before a single negative comes along to pull back down. The positive side gets a head start each round, and over infinitely many rounds, that head start adds up to an extra half of the logarithm of 2. The bookkeeping is identical, the pacing is not. Stop and sit with that, because it should not be allowed. Take 3 plus 5 plus 2. Rearrange it however you like. 2 plus 3 plus 5, 5 plus 2 plus 3, and you always get 10. Order never changes a finite sum. This is the first thing anyone learns about adding. But the fractions just broke that rule in front of us. Same terms. One order gives 0.693. Another order gives 1.04. The list did not change. The total did, and it gets stranger, because 1.04 was not special. There is nothing stopping you from steering that total somewhere else. Pick a number, any number you want, and there is an order of these same fractions that lands exactly on it, not close to it, on it. The sum you get is not baked into the fractions, it is baked into the order, and once the list is infinite, the order is a choice you get to make. To see why this is possible, split the list into 2 piles. Put all the positive terms in one pile, 1, 1/3, 1/5, 1/7, every odd fraction. Put all the negative terms in the other, 1/2, 1/4, 1/6, every even fraction. Now add up just the positive pile, 1 plus 1/3 plus 1/5, and so on. This pile does not settle anywhere. It grows past 2, past 3, past 5, and keeps going. Given enough terms, it climbs past any bound you name. The positive pile alone adds up to infinity. The negative pile does the same thing. 1/2 plus 1/4 plus 1/6, marching upward without end, past every ceiling. On its own, it also runs to infinity. So you are holding 2 bottomless buckets, unlimited push upward, unlimited pull downward. The full series only settled on 0.693 because the ups and downs were interleaved just so and cancelled. Change the interleaving, and you are steering with an infinite supply of fuel in both directions. This is the engine behind everything strange we just saw. If the positive pile had added up to some fixed, finite amount, you would have a limited budget of upward push and there would be a ceiling you could never break. But there is no ceiling. Whatever total you are at, there is always more positive fuel to climb higher and always more negative fuel to sink lower. The only reason the honest interleaved order gave a modest 0.693 is that the two infinities were being spent against each other in perfect step. Break that step, and both infinities are yours to aim. Here is how you aim. Say you want the total to reach the number 2. Start pouring from the positive bucket, 1, then 1/3, then 1/5. Keep adding positive terms, and stop the moment your running total climbs just past 2. Now switch buckets. Add negative terms, 1/2, 1/4, and keep subtracting until the total dips just below 2. Then switch back to positives until you cross above 2 again. Overshoot, undershoot, overshoot, undershoot. The key is that the terms are shrinking towards 0, so each overshoot is a little smaller than the last, each undershoot a little shallower. The total zigzags across 2 with smaller and smaller swings, and it locks onto 2 and stays there. The recipe never changes. Pick your target, pour positives until you pass it, pour negatives until you drop below it. Repeat. Because the fuel never runs out and the steps keep shrinking, the running total is squeezed right onto whatever number you chose. And notice what this recipe guarantees. 2 things have to hold for it to work, and both do. First, you must never run out of terms to pour, which is why the 2 piles each had to be infinite. Second, the terms must shrink to 0, so that every crossing of the target is smaller than the last, and the swings close in rather than bouncing forever. The alternating fractions satisfy both, and so the machine always lands. Every term in the original list gets used exactly once. Nothing is dropped, nothing is repeated. It is a genuine rearrangement, and it hits the mark. And the target really can be anything. Aim at the number 2, and the same fractions reach 2. Aim at pi, 3.14, and there is an order that walks these fractions straight to pi. Aim at 0, and they collapse onto 0. Aim at -10, or 1000, and an order exists for that too. You can even aim past every finite number. Set the target to infinity, pour mostly from the positive bucket, and only occasionally dip into the negative, and the total marches off to infinity and never comes back. This is the Riemann rearrangement theorem, proved by Bernhard Riemann in 1854, tucked inside his work on trigonometric series. The statement is blunt. Take any series that converges the way this one does. Then for any target you name, finite or infinite, some rearrangement of its terms converges to exactly that target. One fixed bag of numbers. Every real number on the line is a reachable total. All you change is the order. Riemann was not chasing curiosities when he found this. He was working out when a function could be built from waves, from sines and cosines, and he needed to know exactly how fragile these infinite sums were. The rearrangement result fell out as a warning sign, a marker of just how little you are allowed to assume. It says that for this whole class of series, the phrase "the sum has no meaning by itself." There is no single answer sitting there waiting to be found. The answer is manufactured by the order you impose. So is every infinite sum this slippery? No. There is a clean dividing line, and most well-behaved sums sit on the safe side of it. Take the series 1 minus 1/4 plus 1/9 minus 1/16, the alternating sum of 1 over the squares. It settles on pi squared over 12, about 0.82. Now try to rearrange it. Shuffle the terms into any order you like, and the total does not budge. It comes back to 0.82 every single time. The difference is the size of the terms. For the squares, even if you make every term positive, 1 plus 1/4 plus 1/9, the pile does not run away. It adds up to pi squared over 6, a finite number, about 1.64. There is no bottomless bucket here. The total upward push is limited, so there is nothing to steer with. When the terms shrink fast enough that even their sizes add to something finite, the series is called absolutely convergent, and order stops mattering. Rearrange all you want. The answer is fixed. That word from the theorem, converges the way this one does, has a precise meaning, and it is the whole story. The alternating fractions converge to a sum, but the sizes of the terms, 1 plus 1/2 plus 1/3, that pile does not converge. It is the plane harmonic series, and it runs off to infinity. So the series converges, yet its terms are not small enough to add up on their own. That is called conditional convergence. The convergence is real, but it hangs on the delicate cancellation between the positive and negative terms. And that gap between a series that converges and its sizes that do not is exactly the room to maneuver. It is what fills both buckets. Absolutely convergent series have no gap, so no freedom, one fixed answer. Conditionally convergent series have the gap, and the gap is the freedom to hit any target on the line. The squares are safe because their sizes add up. The fractions are steerable because their sizes do not. Come back to where we started. 1 minus 1/2 plus 1/3 minus 1/4. Written that way, it sums to the logarithm of 2. But we have seen that this is not a property of the fractions. It is a property of the fractions in that order. For a finite list, adding up the numbers is a complete instruction. For an infinite conditionally convergent list, it is not. Saying add up these terms does not pin down an answer until you also say in what order to add them. The order is not a formality. It is part of the definition of the sum. That is the quiet warning built into the foundations of analysis. Infinity does not obey the arithmetic you grew up with. A rearranged sum is a different sum, and the innocent-looking instruction, add these fractions, only has a single answer once you decide, and commit to, the order in which they line up.